Hi, so we'll be starting at around like 4:45 because like we have to wait for people to come to the link and filter in. Is that all right?
Yeah, fine with me.
Okay, thank you. Hi everyone. Welcome to the Driverless Tech Talk. We'll be starting in a minute or two. Hi, Cindy. Okay, so I think we can start the tech talk now because it's getting close to 4:45 and I don't want to overstep the 10-minute delay we already have. So yeah, you can just take it away from here.
Awesome. Thanks, Vivian. Hey, everyone. Thanks for coming to the Driverless Tech Talk. Let me just share my screen really quickly. So again, thanks again for joining. I'm Cindy, and I'm actually the team captain of the MIT Driverless team, which is a part of this, for school-wide collaboration of different schools that get together to participate in autonomous racing. I'm a first-year MBA student at MIT, and previously spent a lot of time working in the autonomous vehicle space. So, more than happy to answer any high-level questions after the presentation. So, just to kick it off, really wanted to spend a few seconds just outlining our mission. And so, we're a group of students. I pretty much got together over our love for racing, and then same thing with our love for just getting to know about autonomous technologies and then applying them. So we pretty much serve to be the hub of practical autonomy across 4 different schools, just to provide students with opportunities to get their hands dirty, like build some cool stuff, and have some fun at the same time. um, who we are. We're made up of 4 different schools. And, as you can see here, it's MIT, RIT, Pitt, and University of Waterloo. Together, we make up around 40, 50 students across various degree programs. The other thing too is, we're not just a US centric team. Like, we have members that also not a part of these 4 schools but are around the world. I think one of the unique things about our team is that we're pretty much open to anyone that's interested and willing to build some cool stuff with us. And so I know a lot of y'all are high school students, and so as you get into college and start the next 4 years, if you're ever interested in joining, our team can we'll welcome you with open arms. And so what do we do? I mean, if it wasn't clear already, we race autonomous cars. And so as you can kind of see in the picture here, we actually have a life-size Indy car that we went out and bought. And this is the one that kind of just travels with us to Indianapolis, Las Vegas very recently, and then maybe Detroit in the fall. And like the Indy car is part of the Indy Autonomous Challenge, which you can kind of see on the bottom right corner. And one of the other races that we also participate in too is a series called Robo Race. And you can kind of see it on the top right corner. As of now, a lot of the competitions tend to be in a more simulated environment, but hopefully we'll have an actual physical car sometime over the summer. TBD on those details, but this is pretty much what we spend a lot of our time doing. And so for me, what do I do? I think there's as one of the team captains, like, we always like saying that we do a little bit of everything and at the same time we don't really do anything. So overall, I'm responsible for 2 things. One is to obviously be able to win races and to and that tends to be a little more short term, meaning race to race, but longer term, I also work really hard to ensure that, this is a team that it continues to exist long term. And so, we really do trace a lot of our history back to, I want to say, around 2018. So we're not a, we're not a very old team. Like, we only just started a few years ago, and it's just been incredible to just, start from, Formula One 10th to all of a sudden just like having an actual Indy car that we race. And some of the other things I do is I spend a lot of time talking to people, so race organizers who pretty much provide a lot of the information that goes into building the team goals, and also spend a lot of time working with our engineering team and setting some of the technical direction of the team. And then there's also just, trying to bring in new passionate members to the team and making sure they're feeling welcomed. And, like I said, chances are, if some of you are going to college, like, we might cross paths. And, if you're interested in joining, I'd be the one sort of just like working with you and trying to get you set up. And then lastly, one of the biggest things about our team is that so we pride ourselves on being entirely student led, meaning we don't really get much funding from our schools. And so a lot of the money to really be able to build a lot of cool stuff comes from a lot of fundraising. And so you'll often find me just, trying to pitch the team to companies and raise money. I mean, just to put it into perspective, that car that I'm sitting on is a $1.2 million car. And so it's taken a lot of effort and, a lot of just like working together with the broader team to, make sure that, one, we have the talent and we have the resources, but also have the money to be able to get us to where we need to go. And it sounds like it's a lot, and it often is, but honestly, it's such a great group of people that it's really worth like pushing through. And so, this is our car. And so we actually have a Delara AV21. And as you can kind of just see on the left, it's, fitted with a lot of sensors. So we have radars, LiDARs, and cameras. And, we also have an onboard computer, 64 gigabytes of RAM. We have an Intel and an NVIDIA as well. And, it's a pretty hefty piece of equipment. And, we, all of us would, all of which allows us to, have the vehicle race autonomously. Again, like, one of the things I'll echo is that, we didn't design the sensor suite that went into this vehicle. We actually just bought the car with all the sensors. And so a lot of the stuff that we do is just focus on, really building the software. And so got a race car, that sounds great, that's cool, but how does it all actually work? And so there's 4 different components to our software stack that allows our vehicle to just go do laps around the track and race with other cars. And these are the 4 that are pictured in the on the slide. So it's perception, state estimation, path planning, and vehicle controls, all of which I'll dive a little deeper over the next couple of slides. So the first one is perception. And so this is pretty much about detecting the outside world and, really trying to get a sense of what it looks like to the car using the sensor suite that I just mentioned earlier. So for example, in the bottom right, we have a yellow boxed car that's outlined there. And so our vehicle needs to be able to, one, tell us where it's going, 2, how fast is it going, and then 3, most importantly, whether or not it'll crash into our vehicle. And so, we use a lot of algorithms to identify other cars and, really estimate where their position and orientation are. And really, like, we use a lot of edge detections to find lines. And so imagine you have like this black and white pixelated picture where each and every pixel is assigned a value. And, in the areas where some of those values change, we usually call that a line. And you can do all sorts of mathematical operations on pictures, which are kind of just portrayed as grids, to easily figure out where some of these edges are. And, then use that to sort of say, okay, here, like, there's something going on, therefore I'm going to box it out. And then you'll really see that on the bottom right picture. And so there's a lot of like AI and machine learning approaches that you can use. For us, we really just take a bunch of images and then, a lot of the data that we have, we label it so that the algorithm knows what is true, meaning what is a vehicle, what is a person, et cetera, and then feed it into it and train it. The algorithm then filters out what is true and what is not. And so there's a lot of stuff going on there. But I think it's always helpful to kind of see it in action. So I'm just gonna, like, hopefully this works, play a little video that kind of just demonstrates how our car would detect another race car on the track. And so you'll kind of just see it there. And so that's pretty much at the heart of our perception part of the stack. Just pause it. The next piece of it is estimation. And so what happens if you can't see the other car, either because of sun glare, for example? And it's funny, on the track, we do run into a lot of issues where the car is blinded by the sun. Or the other thing too is what if one of your other sensors fails? What do you do then? In the case of a sun glare, if your car is blinded, it might get confused and crash. And given that you're going at 140 miles per hour, crashing can completely wreck your car, and you'll pretty much be out of the race for a good amount of time. And so, how do you counter and correct for that? And we saw for a lot of these issues using what is called a Kalman filter. And, we have one for ourselves to know where we are, and then other cars will have them to know where we are. And so, before I get into like how this kind of works, I think it's important to keep two things in mind. And so one, when you're taking in measurements, all measurements come with some degree of noise. And so if you think about your GPS, your radar, and your LiDAR, all of these will have some noise or error. And so, we have to kind of characterize how big that error is and then what that noise exactly is. And so the second piece of it is we also know how things move. And so if a car is going 60 miles per hour, you can pretty much just say like it'll be a mile down the road in a minute. And so Newtonian physics tells you where things are moving, and that'll be at speed times time equals distance. And so given all of that, a Kalman filter will help predict where the car should be based on, where it's been, how fast it's moving, and then give you a prediction of where the car will be at a certain point of time. And so for us, like this kind of helps us eliminate some of the noise from sensors to predict the true state of where the vehicle is. And then, so where we are, where the other cars are. We know like the bigger question is, once you kind of get into racing, is, well, how do you get around without hitting them? How do you know which is the most optimal path to take without putting the car at risk of crashing? Because again, when you're racing, like you're going up against other vehicles and you're going at such insane speeds that you need to adequately, plan a path for which your car should take. And so, normally in racing, a race car driver will tell you what the optimal path is, but a robot like our race car can't. And so if we're doing a time lap, meaning you're just going around the oval just by yourself, we only have to worry about following a line, and that'll be great, easy and simple. But in reality, again, there's other cars out there on the track. So how do you deal with that? Well, we could make a grid of points on the track and then make a bunch of different paths that connect through those points. And so you can kind of just see like the little grid here on the right where, you have a lot of different paths that you can kind of just draw a line through. And so, what we do is something that we call a search, which means going through all these different paths and then eliminating the ones where the likely outcome is either hitting another car or getting too close to another car. And so, afterwards, you kind of just filter out all these different paths that are just not going to be like a great one to follow. And then you kind of just keep the remaining ones that will kind of allow us to be as close to what we think is the optimal line, which I should have mentioned earlier. So the optimal line would be like this one in blue. And so you want to try to stay as close to the blue line as possible, but at the same time, you also want to account for, what the other cars are doing. And so, really like we're doing that multiple times a second, and it's a continuous are things that are done, just very, very quickly. And so lastly, so, we know what the world looks like. We know where we are at a certain point on the track, and then we know how to optimize for an optimal path. How do you actually drive the race car? Like, how do you actually get the algorithm to, push the car forward and actually drive the car? And so there's what we call like a PID, which is like a proportional integral derivative controller. And before I get into that, I think when you think about a vehicle and just like the controller overall, there's two pieces to it. There's the wheel, which tends to be the most difficult one to manage, because it's, if you're going at 150 miles per hour and like you kind of just jitter the wheel a little bit, like you're done for. And so it's definitely a lot, more complex to manage. And gas and brakes are pretty straightforward. It's just like, you just press and release, press and release. But with the PID, this is an algorithm that takes charge of moving the vehicle, by calculating a value, for example, trying to figure out what the steering wheel angle is, from an error calculation. And I think, it's going to be a little complex to kind of walk everyone through it, but I think the visual on the right kind of helps, put it into mind. And so if you look at the chart here, I guess like the x-axis is sort of like the seconds, and then y-axis is like the miles per hour. So like 0.5 would be like 50 miles per hour. 1 is 100 miles per hour. And so in an ideal scenario, you would want to hit 0 to 100, within a second. Obviously, it doesn't work like that in reality. And so here, like, each and every line represents a different controller. And so there's like 3 signals that this algorithm takes. The first one, which is what is called the proportional, which is sort of like the difference between where you are and where you want to be, and how you sort of start to close that gap. And then the second and the third tend to be sort of like the derivative and the integral of that difference. And so like each of the lines represents a different controller with different signal gains. As you can kind of see here, so the goal is to kind of just be as close to the blue line as possible. When you look at this, it looks like, oh, great, like the red line is probably the best controller to use because it's the closest to the blue line. Issue is you start going from 0 to, I want to say it's around like 120, 130 in about 4 seconds, which is great. But then you start seeing like the steep decline in speed, and then you start going up, and then you start seeing some oscillations. Oscillations is the main number one thing you want to avoid. And then you have this black line over here that, takes roughly around 6-7 seconds to get to that 130 miles per hour, which is great. It looks very smooth, but when you're racing, you want to sort of try to get to that 130 miles per hour sooner rather than later. And so the happy medium is sort of somewhere in between the two. And so, in this case, we would go with the green line, which takes a little longer than the red, but at the same time, you don't see as many of the oscillations as you do in the red. And so I think there's a lot of science that kind of underlines just a software stack, I think. And so like I kind of want to like just have some visual demonstrations. And so try to lower the volume. Hope it doesn't blow up your speakers, but this is an example of our car going 138 miles per hour in Las Vegas a few months ago. Like, as you can kind of see, like it's fairly smooth. You don't really see any oscillations. And it also looks much slower than it actually is. I think one of the surprising things when you're like on the track is that you have these vehicles going at crazy high speeds, but when you're looking at them, it doesn't really look like it's going that fast, but that was clocked at 138. That's sort of like the rosy side of it. You also have instances where, like here in this example, where, sometimes things don't go well and like your car actually ends up spinning out. This one has no volume, but you'll see where like the vehicle just starts, spinning out, going a little out of control. Thankfully, there was no damage. And the reason why we actually spun out was just because I think there was a bug in like the perception code. It was something very minor, but these things happen, and it's important to sort of just be aware. It kind of just reminds you that in a racing situation, like every single little thing matters. Thankfully, we didn't end up crashing, but there were other vehicles at the time that ended up spinning out, ended up crashing into a wall, and then we're left with around like $20,000-$30,000 worth of repairs. And so what have we been up, where have we been and what's next? And so, as I mentioned earlier, we've been participating in the Indie Autonomous Challenge. The first of the, I guess, like the installments was back in October. We raced again in Las Vegas, and we're expected to have a third installment of the race sometime in September, October, TBD on locations. But for the next race, it'll sort of be passing with other vehicles on the road, and yeah, like it'll, like, we're excited for it. Haven't received final details on the race format, but in the meantime, like, we're gonna keep trying to improve our software stack, and hope to be able to reach the finish line at the next one. And so really wanted to say thank you for taking the time to listen to our tech talk. Again, if as some of you head into college, if this is something that interests you, like, feel free to drop in an application. You can easily find us by just Googling MIT Driverless, and the application will be one of the things that comes up. So, wanted to say thank you, guys. And just to answer one of the questions, so when you make all your calculations, do you account for all the rubber on the track? So that's a good one. I don't, so I'm more on the business side and don't necessarily have much visibility into that. But as far as I'm concerned, like, we do have, like, we do account for all of the things related to, like, tire temperature and then warming up the vehicle, and all these racing specific things are accounted for when it comes to deploying the vehicle on the track. But hopefully that provides some insight. But yeah, thanks everyone.
Okay, thank you, Cindy, for the tech talk. It was really good to hear from you. Okay, so workshops are gonna begin soon in like 5 minutes. So if everyone could go back to the track they were on. And